Okay, so is there a possibility? Great. All right. I'm using Zoom to record this session. And hello, this is your astronomer Maria, and I moved a few months ago to Rome in a pursuit of postdoc in astronomy. And today we are going to have fun about talking about coordinates again. And I am plugging in a shameless plug, a totally shameless plug, but people, I want a permanent job in astronomy related career. I'm suffering there. In astronomy. It can be in an institute, observatory, teaching. So if you know of this solution, if you have something, please let me know. Contact me because I'm interested. I moved here with kids, so it is so hard to move. I don't know how I can move again, so I don't want to. I won't be able to move every year or every 2 years or even every 3 years. So I need to find something more permanent and settle and have some stability. Fingers crossed. But back to coordinates. Um, so let's see how it's gonna work. Um, let's bring a bit more light, and this we can. Nice. Okay. Okay. All right. So I did a short, but now with Zoom, I can do a long form. So first of all, we have the Cartesian coordinates or orthogonal coordinates. You can have um, a 2D, right? X, Y, and then 3D, the Z axis. So any point can have in this system, if it's a 2D, two coordinates. If it's 3D, then it can have a third coordinate. So then you can have another type of coordinate system, the polar coordinate system. So that's when you have kind of a circle. Okay, see how can I stabilize? And your first coordinate is r, the radial, and your second coordinate is the angle. So in this scenario, then you can take the r and have its projections for x and y axis. And because it's a right angle, you can use the right angle definitions for cosine and sine to then transform your x coordinate into polar coordinates and your y coordinates to polar coordinates. So I remember from my high school in Armenia, you know, Giteci Haraberitsin is the cosine, when the adjacent side over the hypotenuse is the cosine of an angle, and the side in the front, Dimaseji Haraberitsin is uh, sine theta. So the in front of the angle, that side, if you divide by the hypotenuse, then you get the sine of that angle. So definitions allow you to transform back and forth between r theta coordinate system, the polar coordinate system, and the xy coordinate system. And this is then the basis to go further into what's called the spherical coordinates, where you have a three-dimensional situation, and you have three coordinates. So each point is described by three coordinates: a radial distance, polar angle, and azimuthal angle. So how does it work? So if you have a point, this is your radial coordinate, the r, and then you have a theta, which is the polar angle, and azimuthal angle phi. And there are different variations of naming, but in essence is three. One of them is related from the z-axis, and the other one within the plane of x and y, the other two coordinates. So if you create the projections here from the R onto the plane formed by two of the coordinates x and y and z. Arbitrarily, we can choose x and y. And if you use again the right angle rules, then you know that this is your R sine theta, because this is theta. Can you see? This is theta, this is theta, your polar angle. This is also polar angle. These are parallel lines crossed by another line. So these are the same angle. And so this is your R sine theta, and this is your R cosine theta, which you can barely see. But then right away, you see that R cosine theta is the z coordinate. So it's a transformation. And now you have the value for this line, r sine theta, which then you can project yet another time, a second time, onto this x and y plane defined by x and phi. This is a right angle here. So you can then use the angle phi to get your x coordinate transformation, which would be, so this is adjacent to phi, so it's a cosine phi and times r sine theta, the value of this line. And then this is in front of phi, so it is a sine phi times r sine theta for the y coordinate. Okay, and I wrote here nicer. I'm bolder, so XYZ, you can have these transformations. And now, okay, the interesting part begins. This is, I didn't have my Z parallel, so I couldn't use it. Um, now, we think when we talk about galaxy surveys, galaxies, anytime you observe the sky, that we describe it as a celestial sphere. Celestial sphere, however, locally, you don't have to think of it as a sphere and have any sort of spherical um, corrections in many cases, especially if your area you're looking at is small. So even if it's, and especially if it's in equatorial areas, we discussed it in a different video, we can locally think that use an approximation of a tangent plane, which is the flat sky approximation. So here, this is like the tangent to this point on a sphere and a perpendicular line to it. And this is the plane defined by these two lines, which is tangential to this point on a sphere. And this is your flat orthogonal system, which is locally a good local approximation for many cases, your flat sky approximation. Okay, and now I will try to demonstrate it. So I have to put my phone, hold on, um, switch back to me. Put like this. Let's see how we do this. Okay. Um, so this obviously a sphere is a 3D object. A 3D object. So when I draw it on a paper, it's hard to imagine. So here is my celestial sphere mock simulation. This is orange from Frascati, Italy. So when I talk about tangential plane, sorry, there's a glare on my glasses. Um, uh, this is what I mean. If there's a point, the tangential plane, uh, my ruler is no longer here, but the line would be, if there is a point, the line would be tangential line this way. But if you put a paper, that's your tangential plane, and this is your flat sky approximation. And then on this paper, I can do my XY coordinates. Um, but I think there is even another way we can um, have a feel about how it is the flat sky approximation, the tangential plane approximation, how it is appropriate for local small patches. So if I draw, let's say I want to know this patch. Okay, let's see. Have some light on my orange. Is it gonna work? Moment. I'm trying to draw patch of sky. I think I need a marker. I'll go get a marker. Here's my marker. Come on, orange, work with me. Okay, perfect. I can draw a little patch. So let's say I want to study the galaxies on this patch of my orange sky, orange celestial sphere. This is my north celestial pole. This is my south celestial pole. Let's say this field is equatorial. Equatorial. So I have kind of a slice between two longitudes, so to speak, and then between two latitudes. Can you see? So if I take my knife, right now it is spread on a spherical surface. But if I cut, see, can I cut nicely without cutting my fingers? I'm cutting along these lines. So I'm cutting along these lines, which kind of hug the contours, the borders. And then I hope I can almost. Um, patch is still described by these lines, but I removed them from the hugging the spherical surface, and I brought them into the tangential plane from that little patch. And locally, you can see that this tangential plane, defined by these two axes, is perfectly okay for this small patch. In some cases, if it's small and equatorial especially, to be described by this tangential plane, because I don't care about these coordinates here or these values here. I'm only here. This is the area I studied. It is still on a sphere, and it's still also on the tangential plane defined by these peels, basically. So the difference is very small. Um, and in many cases, you can just use this flat sky approximation. Maybe I try to, uh, you know, rotate it. So you can see this flat sky approximation is valid. So you can use it to describe your little patch of sky on your celestial sphere, and you don't need to um, include in your calculations the spherical um, any consideration for the curvature. So you can just think that this is a flat sky because the flat sky spherical model, spherical coordinate system, and the flat sky system, they coincide quite well locally in this little patch that I colored in black. All right, so thank you, Mr. Orange. Thank you for your attention. And science is fun, astronomy is fun. Let me know how you think about spherical coordinates or anything. And God bless you, and eat a lot of oranges so you don't get sick in this cold season if you live in a cold season, winter area. And Happy New Year, everybody. God bless you.